Welcome to the UQ School of Architecture Architectural Technology courses. In this series we will be talking about the regulation of energy use in buildings to reduce greenhouse gases with reference to the Australian National Construction Code Section J. Section J makes some assumptions about the way occupants will use buildings and the way they consume energy. Typically, users of Class 2 buildings, which include apartment buildings, have to pay for the energy they use. In contrast, people occupying Class 5 buildings, such as offices, will not be involved in paying for the energy used in the building, and thus have a lower stake in the effects of excessive energy consumption. In simple terms, if you pay for the energy, you are most likely to conserve the energy you pay for. Lighting is a good example. In Class 2 buildings, users have a direct relationship with the way they consume energy for lighting, as compared with lighting in an office building. As a result, Section J tends to look at control systems in Class 2 buildings as user-operated when they are within the domains that they control and care about, whereas other strategies such as timers and sensors are needed for Class 5 buildings where users consume energy more passively. Another aspect that is often overlooked is when considering standardized buildings and the impact of positioning these in different climate zones. Aspects that can be controlled, such as orientation, play a significant part, but increasingly it is the invisible aspects of building performance that play a major role, such as the specification of insulation, wall construction, glass types, and glass assemblies. When developing an alternative solution to comply with Section J, proposals are benchmarked against a reference building that complies with Section J. The alternative solution must on balance perform as well as the reference building, which opens up some scope for design trade-offs. For example, the alternative building may not perform as well as the reference building in some aspects, but may perform far better in others, which on balance results in a complying alternative solution. Building fabric is a key aspect of overall thermal performance. It is essentially the capacity of a building envelope to reduce the flow of heat from an internal warm environment to a cooler external environment and vice versa. Comparing a Class 2 building to a Class 5 building though, the effect of a high-performance envelope is greater in a Class 2 than a Class 5, simply because there is more building envelope in relation to glazing. The building envelope in relation to performance under Section J may not be as immediately obvious in a Class 5 building. For example, the roof may contain building plant and equipment, whereas the basement or ground level may be given over to car parking. In these instances, the envelope that needs to perform well thermally is the threshold between the habitable space and the surface areas. We need to be especially cognizant when services transition between the inside and outside and make sure we do not compromise the envelope integrity. The definition of inside and outside is also important when we consider roof voids. Architecturally, it is always great to express large open volumes, but we must be aware of the impact this will have in defining the envelope and the volume of conditioned space. Other aspects to consider also include the position of surfaces in relation to the external envelope. We need to consider what side of the envelope the surfacing sits, as well as recognizing the necessary safety clearances around heat-generating equipment, such as lighting fixtures. These clearances break the integrity of the envelope, and the accumulative effect of these breakages are factored into the Section J calculations. Typically speaking, many facade contractors and manufacturers of certain building materials will provide data relating to the performance of wall assemblies. Manufacturers will usually also be willing to assist with a calculation of transmission values, such as the overall U value of a proposed wall assembly. Two dominant forms of insulation that are used to achieve compliance are bulk insulation or reflective insulation. As the name suggests, one uses trapped air to slow down the transmission of heat through a material. Reflective insulation, on the other hand, uses reflective surfaces to bounce unwanted or wanted heat. Sometimes combination insulation types that incorporate bulk and reflective materials in the one product are used to match specific heat flow situations. It is important to note that bulk insulation does not perform to its stated R values if it is compressed. The effect of compressing the material reduces the amount of trapped air and thus reduces the material's effectiveness. As designers, we must ensure instances such as the filling of material in cavities, around surfaces and in roof spaces, that it's not compromised by compressed insulation. Designers need to be aware that the thickness of insulation needs to match the clearances and the sizes of structural elements. Section J1.2 contains tables that outline the conductivity of materials that can be used to calculate the R and U values of wall envelope elements and total assemblies. Wall build-ups can be calculated by adding the component parts of the wall. In this instance, the brick wall is comprised of a layer of brick, an air cavity, timber structure with bulk infill insulation, and a gypsum board inner lining. The other aspect that is included in the calculation that varies between walls and roofs is the insulating value of the air film on the inside and outside of the wall. Inside air films will typically have higher values because they are less affected by prevailing wind and breezes. Surface air films are defined by their context rather than material, and their values can be found in section J1.2 Table 2b. Other aspects that affects the envelope are things such as the roof pitch and roof colour, reflectance and absorbance as a consequence of colour, and the angle of incidence of solar radiation are the factors at play. Section J, Part J2, relating to glazing, has perhaps the most significant impact in the design of contemporary Class 5 office buildings. Facade engineering and glazing technology is perhaps the most sophisticated in this use type, simply because of the effects to overall building performance. Once again, daylighting plays a role in the control of heat buildup inside a glazed facade. Playing off the variable vertical shadow angles between winter and summer can result in solar exclusion in summer to solar inclusion in winter. Glare and reflected daylight need to be considered in the overall picture to ensure that energy controlled in one scenario does not excessively offset energy inputs from another. Said in another way, the need for daylight should be balanced but not dominated by the need to control excessive direct solar penetration. Balancing the amount of direct and indirect light can be regulated through shading of the facade and the zoning of artificial lighting. Light levels in various situations are governed by the Australian standard AS 1680. The lighting level is a consequence of room size, room shape, orientation and so on, which in turn translates into a total illumination power. This illumination power is created by light fixtures and light bulbs that all take a certain amount of energy to run. Different light types consume energy differently compared to the light energy they produce. Compact fluorescent and LED lighting are becoming the mainstay of modern lighting design, as they can produce the light levels needed under AS 1680, whilst also complying with the total energy use under Section J. In addition to this, control systems that automatically turn off lights or automatically dim lights in rooms that are unoccupied all contribute to reducing the baseload energy needed even further. That concludes the videos outlining the regulation of energy usage in new buildings to reduce greenhouse gases. The videos are intended to provide a general overview of Section J and the concepts around which the legislation was built. Detailed calculations are a more involved process and are subject to future discussions.